this video we'll talk about the Ramsberg Osgood law. Alright, this is the equation that we'll be using. Alright, so let's start. If you still remember, the Ramsberg Osgood power law deals with the hardening. Alright, just go back to this. I actually forgot to say. Alright, so this n is your hardening factor, or this c is some constants. Okay, it's talking about some hardening in terms of the material itself. Alright, so after initial yielding at a Von-Mises stresses at 200 MPa, a ductile steel hardens according to a Ramsberg Osgood power law, which is what we have said just now. So therefore, in which the hardening constant is n, n is equal to 0.3 and c is equal to 0.1, and therefore plot the stress strain curve. So in fact, from here you can see that the Osgood power law is somewhat used to plot your stress strain curve. Alright, it's a very powerful tool. Alright, and therefore, how do we start? Alright, so the first thing first, you just sub in your numbers, the equation of the Osgood law. So instead I will write this as the yield strength. This is also the yield strength of the material. Alright, this is somewhat you're very familiar already, your equivalent incremental strain. Alright, so the yield strength itself, as you know, is initially yielding at a Mises stress of 200 MPa. So therefore the yield stress is actually 200 MPa over here, and your n is 0.3, 0.1. Okay, so left with what do we have is go on, be very careful. He's talk about Mises stress, talk about Von-Mises, but however it's initially yielding. Initially yielding means that you're talking about the yield strength, which is 200 MPa. So be very careful of the language they use. It's trying to trick you, Matiam. Alright, and therefore what we're actually keen is to plot in terms of whatever your Von-Mises stress would be, or whatever stresses you want it to be. And we just simply rearrange this whole equation in terms of the equivalent strain with your whatever stress that you input. Alright, so you input a certain stress, you'll get a certain strain. That's what it's trying to say. So for example, if you have this curve, you know that this elastic, never mind, we just don't care the elastic. So the curve starts when you input a certain stress over at this point. This is your stress sigma. At this point you have a certain increment of this, you have a certain strain. At another stress you have another strain, another increment of strain. So this is somewhat your increment or whatsoever. Okay, so you just started off with your initial yield strength. So this is your yield strength is equal to 200. You just sub it in into your as your sigma Von-Mises. What you have is you have no strain. Alright, and then you slightly to increase your Von-Mises, or in other words, increase your stresses as well. What we have just say over here, you increase with another stresses, and you see how the strain will increase. Alright, and therefore, as you can see, once you increase this particular stress by 40, you will have an increase of 0.064. And then if you increase by another 40, you have a larger increasing by times 2. If you increase another 40, you have more. So from here you can slowly plot that it may be something like a exponential, I think, but I don't know. So I'll not plot it out for you, but at least it's something fairly useful for you to check it out. As for B, you have given a stress state, so you're asked to find the effective plastic strain. So the same thing, instead of having an incremental 40 by 40 by 40, what you do is to have a stress state, which is what we have been shown over here. Alright, so you just find your Von-Mises stress, that's what we have done all along. You have 339 MPa, and you sub this 339 MPa into this equation. Alright, once you sub this 339 MPa into this equation, your E equivalent will be 0.42. Okay, so you have an increment from there. So it's just straightforward. Okay, then C is to get a 5% increase in the effective plastic strain. So it's just simply talk about last time we do, but take note of the 5% increment. So this means that your particular this thing over here is 0.05% increment, or in other words 5%, which is 0.05 because divided by 100 is 0.05, things like that. Alright, Von-Mises is simply from the part B, because they actually ask you to find that the material, so this material is talking about this material that is subjected to a stress state. Alright, so just let you know lah, okay, then you just sub in your stuff, the devolteric things. It's kind of straightforward. Alright, so just think about it. Alright, once you do this, when you solve this thing, when you multiply in your stuff over here, what you have is all these things. And when you multiply in, you're talking about percentage. This is the first thing that I know. Alright, first time that I see percentage. Alright, so when you multiply things inside your overall, or you multiply this constant into your devolteric system, you have a certain percentage, incremental percentage, I would say, which is what they're talking about. Determine the increase in the plastic strain components, things like that. Alright, this is pretty interesting. Later on you'll see why is it interesting. Alright, same thing, you have some pressure is given, use the Ramsberg Osgood law. When you see C and N, you know that is this Osgood law. Alright, so compute the total equivalent plastic strain, this one, if the material is subjected to a stress tensor, a stress state. Alright, so you have to find this EQ. So how do you find? So this is your Osgood law, if you still remember. Well, just take note that this is your U strength, this is your U strength over here. Okay, language, the metal initially U. So this means that its U strength is 240 MPa. Okay, and then you just simplify your warmnesses. I think you already know it's really something in depth into you already. Just sub in your N over here and your C. Where's your C? I think it's already inside there already. So it's just straightforward, just 0.323. Okay, just simply subbing everything that you have. Alright, just check it out. Alright, but eventually you are trying to find this thing. Your C is given. Alright, which is what is it? 0.12. Alright, it comes as a set. So now the next question. If this one is increased by 2%, compute the plastic strain increment tensor. You see the language where it's talk about the increase by 2%, right, where your equivalent so-called your strain increased by 2%, and how you will see this thing happens, you know that you're going to use some sort of the equation that we have seen earlier, right, which is this one, I think. Yeah, if you find this familiar, this is your constitutive equation of your plastic stress strain glove. Alright, so the first thing first, we find our warmnesses, alright, and in fact what they find first is actually your devolteric stress. Alright, so it's over here. Alright, this thing is over here. Alright, well, your warmnesses is already 370 because we have found in the previous part stating that is 370, right, at part A. So now you just simply sub in, and just take note that this equivalent now is increased by 0.02. Alright, so this d epsilon EQ is the changes. Alright, well, epsilon EQ itself, if you take a look, epsilon EQ itself is just to say that the equivalent strain, and that's all, some strain. Alright, and then the increment itself talks about the changes across certain time. Therefore, this is or certain changes with other stresses. And therefore, you need to take note of the language they use. Alright, so this is a good question to do with this. Just simply rearrange and things like that. You should get this thing over here. Alright, and micro strain simply means that it's 10 to the minus 6. Alright, because you're multiplying things. In case you don't know what the hell is going on. Alright, for this case. Alright, next. Now that comes the very interesting part. Right, determine the change d sigma m. In sigma m, that will result from this increment of this thing. Ta-da! Alright. Remember you have your Osgood law over here. So talking about d sigma m, this means that you're gonna differentiate your stuff in terms of you're gonna differentiate your dEq in terms of your d sigma m. So in other words, you're going to differentiate in terms of your sigma m. And therefore, it's 1 over n. So if you differentiate one time, 1 over n becomes over here and 1 over n minus 1. Alright? Or the sigma m itself, if you differentiate, the constant you keep is 1, your U stress. Alright? And things like that. I think you already know what I mean already. Okay? Quite straightforward. So this is the part where we last stop, and then you just bring all the way up till here. Okay? So after you differentiate already in terms of your sigma m, you just simply sub in your values, your c, your is this the n? 0.3, yeah, it's the n, and then you just simply sub in all the stuff. Eventually you have this thing over here equals to this, alright, which is somewhat this thing. So you just simply multiply your this thing upwards to all this equation, alright, and then you just simply rearrange, you'll get something like this again. And then since you know that your equivalent is 0.02 from part B, as they say that your equivalent increment has increased by 2%. So just simply sub in all the values, and eventually you have 5 MPa as your change in the sigma volumetric. Alright, so in other words, visually, the small change, this d sigma m over here, give you a change in your d equivalent strain. That's so to speak lah. Alright, so this maybe this part over here, or this part over here, things like that. Alright, so hopefully this gives you a clear understanding of how all this thing get enhanced. Alright, so therefore I think we're at the end of this whole lesson. I shall see you soon.